All right, hello Zoomers, hello Roomers. Welcome to today's meeting, which is CSAW Recap. That is not what I want. I want. Oh, now we do it. Hi. We. So I'm gonna just keep myself off to the side and actually just do that. All right, can everyone hear me on Zoom? Can
Yep.
Okay, cool. Perfect. So this is a mess. Normally it do. All right, cool. So CSAW Recap. Hello. We got second place. That's pretty nuts. We've never done that before. So just for reference, in the past, we've gotten 30-something place, and then we qualify for our bracket, usually in like 13 out of 15 or like 9 out of 10. So what happens there is CSAW gets broken down into different brackets. So there's the US bracket, there's the Europe and India, I forget. There's like a bunch of different brackets, but we not only did we place second in US bracket, but we placed second globally, which is really, really awesome. So we're gonna go over a recap of that. First of all, quick announcements. September fall recruitment event, apologies, has been moved to an October fall recruitment event. We had that in the newsletter for this upcoming Saturday. Maybe we'll try and do like a social event this Saturday to replace the missing recruitment event. That way, if you took plans out, we can do something. But the October recruitment event will allow us a lot more time to have better challenges and just a better event in general. So then the challenge board, the internal CTF is going to get reset today. So here's what that means. Every single challenge that is yet to be released, but is public on the board right now, with the exception of 3 sets of challenges. Everything that's been released since the start of the year, and then Bandit and Not Us. Everything else is going into a category called the vault. So they'll still be up, you can still do them, but there will be 0 points. So at some point during the semester, we will unvault challenges as they become as we need them. And if you've already solved them, then make sure to help other people, but you'll get your points back because we will up the challenge value back to that point. So all the old challenges are going to get their points reduced. And then the scoreboard will functionally be reset, but actually it's going to be reset as if we reset it at the start of the semester. So the grandfathered in challenges, again, Bandit, Not Us, and anything that we've done since the start of the semester. So first command stuff, et cetera, et cetera. So photo dump of CSAW. We had a really great time. It was 48 hours of solid challenges and stuff. For a little bit there, we were actually at like Saturday night at like 1 in the morning, we were beating PPP. So the fact that we were able to do that at all is unbelievable, and it's amazing.
PPP is we were first.
We were first, which is like, we've never done that before. Like, this is the best we've ever been as a club, and I'm really excited about that. So, yeah, so lots of fun photos. In the bottom left right here, here's everyone doing math stuff up on the board. We had an awesome team of people who came in clutch with krypto and kind of just like did math for 48 hours straight and then like solved all the krypto challenges, which was unbelievable. And then even more photos. There's the one I took right when we got first place. It's very beautiful. There's just more photos. At the very end, we watched a video about like a Minecraft hack client. So, that was fun. Also, there was lots of food. So hopefully we'll be able to do that again. I'm going to try and get a sponsor for our future CTFs. That way we can do that without needing to worry about cutting into our budget. challenge walkthroughs. So we're now going to go through some of the challenges and talk about how we did them. So this is actually going to be everyone going around and doing it. So it's not just me talking the whole time. I'm going to spotlight myself that way. Yeah, cool. Cool. That way I can see myself and know. Just look at the camera for everyone who's here. Make sure, look and see that you're in the view. Cool. So who is first? Breaking news, crypto equals math. That is,
Yeah. All right. So today,
check the camera, make sure you're.
I should be in. That is true. All right. So I'm going to be going through 2 of the cryptography challenges that we did for CSAW. It basically involved just a lot of people doing a lot of math for 48 hours. It was great. I had a good time. Yeah. Yeah, I don't know. It was a lot of math from classes like a lot of us haven't even taken, just reading papers, Googling, frantically reading Wikipedia, plugging stuff into the Python, hoping it works. Can't get much better than that. All right. Hello, please. All right. Let's go back. All right, whatever. So our first one was ECC Pop Quiz. Okay, this was essentially we were given 3 randomly generated elliptic curves, and for what those are, you can see the curve right there to the top right. I'm gonna try to move this camera. All right. So an elliptic curve has some very nice properties, and basically the problem we're trying to solve is called the discrete log problem. And probably the best explanation I've seen for it, right, is so the way you have a starting point and another point, the way you add 2 points on a curve is, so if we're doing P plus Q, you do P plus Q, draw the line where they intersect, find where the line intersects again, and this picture is actually missing another step, you reflect it down. And then you just keep repeating this process iteratively. And the best way I can explain to why this is hard, right? Imagine I had a pool table, okay? And without you seeing, I placed a pool ball somewhere, I hit it at a random angle and velocity, I just hit it, and then I showed you what it looked like at the end, where it stopped. And I told you, find where I started and find what direction I hit it. It's possible, but it is an extremely hard problem. And thus, that's where the security of elliptic curve cryptography comes in. However, the whole point of this challenge was to exploit weaknesses in elliptic curve cryptography if it's improperly implemented. So the first curve we got made use of an attack that's literally called the smartass attack. There's a paper written about this. The paper calls it the smartass attack. And this took advantage of the fact that the prime they gave had some special properties in relation to the curve. And that was the first attack. And the second attack was something that's called the MOV attack. That just like says, like, hey, if the primes have a special property, then we can reduce our elliptic curve into a much simpler object. And there are very fast algorithms for solving the problem in context of the simpler object. And then the third one is a singular curve, and you can kind of see with this one. So we were given the parameters for the curve, and it turned out to have a special property called singularity. And because of that, it made cracking the third curve very easy. So essentially, the problem was that pool thing. We solved for the starting position of the pool ball 3 separate times. This was randomly generated each run. You couldn't just run the code once and brute force it from there. We had to write a script that could solve this problem over and over. And that's like the whole pop quiz of it. You didn't know what numbers you were getting ahead of time. And this was due to the effort of a lot of people. Some of them are in this room, some of them are on Zoom, some of them couldn't make it, but a lot of people contributed to this, and it paid off. It was 478 out of 500 points. So not a lot of people overall in CSAW solved it. So yeah, that was ECC Pop Quiz. Does anyone have any questions about elliptic curves? I know it's not a concept that's really taught in any courses, especially in none of like the earlier courses. So, all right. The next one was Forgery, another cryptography challenge. It was a lot of people, but I'm gonna move the camera. One guy, David, he's not here today, but David clutched up. We were all working on it, and he just kind of came in, gave the solution, and then like left. Which, yeah.
He took pizza.
He took pizza and then left, yeah. So he deserves the pizza. Okay. So this one was again solving a very similar problem to a discrete log. The whole crux of the problem really boils down to this equation in the bottom right. Okay. There's a very trivial solution where if M, R, and S equal P minus 1. So P was a prime number, a very large prime number that was given to us. And then G was also given to us. And I think that's about it. Yeah, everything else was our inputs. But P was a very large prime number. And there's a very special fact in number theory where you can take any number, raise it to the power of P minus 1, mod P, and you get 1. Okay? So if you think about it, we were going to use this to exploit the fact that 1 is equal to 1 times 1. That was the crux of the problem. But you can see here that P minus 1 in this bottom left piece of code from the challenge, P minus 1 is not an allowed value. So we couldn't do that. So we took advantage of a slightly less trivial solution, thanks to David. We did P minus 1 over 2. And if you remember with exponentiation, if you divide your exponent by 2, that's the square root. What's the square root of 1? 1 or minus 1. And it turns out if you set M, R, and S to P minus 1 over 2, this works about 50% of the time. So from there, we wrote a script to plug in these numbers. And after 2 tries, we got the solution. So just again, more math, more number theory. Very cool stuff. Props to David again for clutching up.
It was so funny.
Yeah. Hey, I'm not like, we like a couple other people were like working on the challenge. He just came in like, guys, it's just this.
Yeah, he sits down and Michael says, "Do I need to move my stuff?" He's like, "No, I won't be here long." and then he solves it, grabs the pizza and walks away. It was really funny.
Yeah.
Who's up? Oh,
think
it's
up
me,
next.
Andy.
Yeah.
I can do it if you don't. I know you're working on stuff too. Okay, so I'm gonna reset the slides real quick. I have no escape button on my mouse because on my computer because Macs are wonderful and beautiful. What? It's the touch bar is broken. It's like acting up. Can you guys still see the screen? No, can Zoom still see it? Because I literally cannot hit escape. I'll just make sure. Cool. Can you guys see it? Everyone good? Can someone in Zoom like tell me if it's good? Because I can't hear any of you, nor can I see thumbs up and stuff. Hello, Zoom. Okay, we're good. We're good. Cool. So, came to the BACnet. This was a challenge that was an analysis of an old building network protocol called BACnet. And one of the sensors was acting up really, really bad, and the flag was the sensor's name. So it was flag sensor name. So we actually had 2 methods because 2 groups solved this within 5 minutes of each other. Pete solved it first, and then we, myself, Anusha, and Faisal solved it about 3 to 4 minutes later. And we did not realize that. So the first step is the manual analysis, which is what I did. And this is a good way to kind of go through this from really knowing nothing about the packet structure. So the first thing that we did is we got the names of all the sensors. Then we found the values associated with each one of those names. Then we isolated those values, and then we figured out which values were acting up. So the first thing to do is just look at the packet and figure out what was going on. There's a lot of information, but what you can see here is that the most of the messages are being sent but from 2 IPs, 159.40.50 and 159.40.200. So it's going back and forth between those two things. And also, it looks like there might be a pattern over here for how this is working. I didn't know anything about BACnet, so I went at this just from pure forensics, just like how can I understand what's going on in this packet. So the first thing to do was, again, get the names of the sensors. So to do that there was to load the object names JSON dump. I'm going to show you how to get that in a second. Then you just go through the object names and find it, and then get it and add it to just a text file. So to actually find that, you can actually use a, what the heck? Where did that slide go? Oh, that was weird, jumped over it. So you can filter, to actually get that list of packets, get object names, you can filter by BACnet, which is a thing that comes, it's a filter type that comes with Wireshark, and then you can get object name. And what that just does is says, okay, let's figure out where object name exists, so where it is not null. Then it filters by that, and as you can see in the top right here, it's just all object names. And then from there, Wireshark has a neat little feature where you can actually export a filtered list to JSON, which there's other ways to do it, but JSON is the way I know how to just do it really quickly, because in Python, you can just load things from JSON as a dictionary. So you take that, load it into a dictionary, and take that dictionary and filter out all the names. And you just get the names that are new. And what that results in is like a list of 10 sensor names and like 30 other PLC names. So this is important because we're gonna cover something at the very end of this. So next thing you do is find the values associated with the objects. So I looked at the very first message, and I noticed that in between right here, there's the object name for package 1, and then at package 11, there's another object name. So if you notice here, it looks like there's a loop, like a standard loop for how communication is done, which is a really common thing within networking, where you have send a message, receive a message, and like acknowledge that message, and then that loop continues again. So the loop begins with a send request object name, and then get object name, and then request units, get units. Again, then get the event state, and then out of service, and then get the present value. So we can you can kind of draw the reasonable conclusion here that if you have an object name right here, the value of that object name will be at the bottom right there. So to do that, don't even try reading into this. There are a bunch of different ways to do it. To get all the actual values, the two methods that I tried, one was that the length of the present value packet was 65. So you could filter by that. That turned out to be ineffective because there was no way to associate the name with the actual packet. So what we ended up doing is noticing the names, the response of the packet. If you look at the packet 8 after that, it will give you the actual value. So you look at that there, and it dumps the object values. So then here's just the dump, and it's all compacted down, but inside there's a ton of values. So then you can analyze those values using just, means, medians, range, all that stuff. Take a look at that there. And the one number that really sticks out is the mean of 21,160, and then the range for sensor 1, 2, 3, 4, 5 of 98,594. The range is really what sticks out because what that means is, hey, something's really fluctuating here, whereas all the other ones are fluctuating maybe 18 or 9 or even 0. So it's something that's fluctuating a ton is probably going to stick out. So if you look at it here, sensor 1, 2, 3, 4, 5, totally fine until 99999 for a few seconds there. So the flag was flag sensor 1, 2, 3, 4, 5. Oh, the other way to do it was with PyShark, and this is what Pete did. And he basically did the exact same method, except he loaded it into a Python framework called PyShark. The point of showing both of these methods, we're not going to go into the other one, but it's basically the exact same thing. The point of showing both of these is that there's always a manual way to do something, and there's always a more automatic way to do something. PyShark helps filter it quickly, and it would group those messages that are being sent automatically. But at the same time, it's important to know both of those things, because sometimes there'll be a completely new protocol that Wireshark doesn't even know what to do with. So being able to analyze it manually and figure it out is just as important as knowing how the tools work when you find something that you know exists already with those tools. The last interesting thing was there were 10 names, or 1, 2, 3, 4, 5, 6, 7, there were 8 names. So you could only guess this flag 2 times because the search space of flags was only 8. So it was quite interesting because if you looked at the solution page, you could see accounts that had solved it. There were a lot of solves on this one. It was only 50 points. But you could see accounts that were brand new and only existed for the purpose of, oh, I have a solve on pain in the BACnet, which means that there were teams that were solving this challenge by testing all of the flag options. So it's kind of, funny cheese answer that got some people disqualified, but it's something to consider. All right, Kevin, you're up for like a bunch of these things. Let me just make sure recording's good. Cool. And then just check yourself on the camera.
Yeah, cool. So, yeah, I'm going to be talking about the 3, I guess, like hardest pwn challenges of the competition. Well, what is it? Oh, okay. It looks rainbow, but it's a lot of colors. Okay, so I guess first I'm going to kind of go over what pwn like even is, because I'm not sure like all of you are familiar with that. Or how many of you know what pwn the category is? Yeah. Okay, so it's like pwn is kind of like a hacker slang term, I guess. And a more descriptive name for it is binary exploitation. And a binary is the compiled version of a program. So when you're writing code in like low-level languages like C and C++, which are, I mean, relatively high level, but for our purposes, they are like low level. They are converted to machine code that the processor directly executes. And then binary exploitation is the challenge of kind of making the processor misbehave with how it's on like the very, very low level of the like raw machine code instructions that it's doing, where you have like numbers that tell the processor what to do and control what circuits are taken within the CPU itself. So, and for that, we look at assembly code, which is essentially a like almost one-to-one representation of the machine code, the actual bytes and the numbers that the processor sees, but converted into human readable kind of strings like add or sub or like move. And so that you get a binary that you can then convert into assembly, and that's kind of the closest thing that you can actually read and interpret. When we're actually solving these challenges, though, we often want to get an idea of what the binary is doing, and assembly is very, very verbose because you just have these single one-line like instructions. You don't have any control flow things other than jumping to other lines. There's no like indentation or like loops or whatever. It's just a jump instruction. So then there are these things called decompilers, and the NSA released a fairly good one for free a few years ago called GDRA, as they pronounce it. And that essentially converts your binary into assembly and then into some kind of C-like code. And this right here is some C-like code for the program Cold, which was a 498-point pwn challenge. So I guess a basic overview of what the program does is that it decompresses a string you input. And decompression is kind of a silly name for it because the string ends up being longer than what you get out, but that's what it calls it. And what it ends up doing is it takes the string and it reads in the bytes. And here you might have, or actually it reads in bits. So it has this bit stream class. And you can see the struct here. This is actually a write-up from a friend of mine who was on, or this screenshot is like code, pseudocode, I guess, of the program written by a friend of mine that was on a different team during the CTF that did a write-up after I like helped them solve it after the CTF was over. And I'll actually like send a link for that in the Discord because it's a good write-up. But basically you have a bit stream class that has a basic string view. And then a basic string view, you can see it's in the std : that's like a namespace. So this is a libc function where libc is like a library, a standard library that is generally shipped with systems that you can use from your C or C++ code. And in this case, it stores a string and it stores a length of that string. So we're storing a bit stream that is basically a string and then a number that my friend called the needle. And that's the location that you are in the bit string. And we can see in this code, I wonder if I can zoom in, that's fine. So essentially it gets a single, or it gets 3 bits. So you have a 3-bit long thing from the user input, and then it switches on that value. So if it's 0, then it just returns, it exits the program. If it's 1, then let's see what that does. It gets a bit, and then it appends that bit to parameter 2. So parameter 1 is going to be the user input, parameter 2 is going to be the output of the program. So this copies a bit from the input to the output. Number 2, how do I scroll down here? We can get 8 bits, and then we can append 8 bits. So param 1, then param 2. So this is like the same deal. It's just taking bits and appending them. This time it's a whole byte, because a byte is 8 bits. So that's useful. Case 3, this is a weird one. We'll come back to case 3 later. Case 4 is going to, this one's also a little bit weird. We can see that it reads 16 bytes from parameter 1, and then to parameter 2 plus 16, it writes parameter 2, it writes the value at parameter 2 plus 16 plus the value that it read from the original one. So I guess this is like a, so parameter 2 is a bit stream structure, okay? And then, yeah, there we go. Well, plus 16 is actually going to be our needle. So this is offsetting the byte. Okay, well, we can look at this. Basic string view, it consists of a uint64t and a pointer, both of which are 8 bytes. 8 plus 8 is 16, 0x10 is 16. So at a 16-byte offset from our bit stream structure, we have the needle, which is the index of the bit that we are currently looking at in our bit string. So then over here, what this does is it reads 16 bits, and then it writes to the index offset of the bit stream, of the output bit stream, that the number that it read from the input plus the current offset from the, from the bit stream. So essentially, this is just jumping forward in the bit string where we're writing. Yeah, and then there also is bounds checking, which will be important. And the bounds checking is checked by checking the length of the string that is contained within the bit string. And I didn't get that code in here, but the bounds checking is like right below. There's a do while loop around this. So first off, I'm just going to start, jump right in. This was my solution, which is a little bit, I guess, compact and hard to read, but we're going to kind of parse it out and get a general overview of what it's doing. So this bit of code, I said we were going to come back to case 3. This is very important. This is kind of the key to the solution. So we're going to look over this. We get bits. We get 10 bits. Now we go, first we get 10 bits from our input. Then we get another 10 bits from our input. uvar3 is the first 10 bits. uvar4 is the second 10 bits. Then we say that, well, uvar4 does not equal 0. We're going to decrement it. So we're going to do something for n times, where n is the second 10-bit number that we read from our bit string. Okay, now we're going to get a bit at a specific offset. So from param2, which is our output bit stream, we're going to get the one n bytes, or I guess I'll call this like this uvar3 bytes before the end, because if we remember, plus 0x10 is the offset of the current position in the bit stream. So we're going to go uvar3 bytes before our current position in the output bit stream. We're going to read that byte, then we're going to just append that to our output bit stream. So essentially, this is just duplicating a bit from an offset from the current location of our needle in the bit stream. And we're going to duplicate that however many times we say we want to duplicate it with uvar3. And okay, this looks fine, except does anyone know the problem with this? So the bounds checking, remember, happens outside of this block. It happens at the end. Most of these operations, you can only do one read or write. So you're only going to increment by whatever number of bits, and it's no big deal. If you go out of bounds, it'll just get caught on the next iteration. However, here you specify the number of iterations that you are doing within this block that no bounds checking occurs in. Okay, there we go. Yeah. So now, since now we can just make this a really big number, make uvar4 a really big number, because we control that. and then we can just write a ton of bits, a ton of ones, just like beyond this, beyond our M string pointer, wherever that is in memory. So what can we do with this, I guess? We can write out of bounds of our pointer. And the question of what we overwrite depends on where our pointer is in memory. And where is it in memory? Well, normally you would expect it to be on the heap. And I guess I'll talk a little bit about like the heap and the stack. So you have like basically two kinds of memory usually when you're dealing with these low-level programs. You have your stack memory and you have your heap memory. Stack memory, it's allocated every time you call a function. Functions have like local variables, right? And you need space for these local variables somewhere. And the thing is that when you call a function, you know what local variables you need, and you know how much space you need to allocate for them. So it simply takes up some space on the stack. You have like your stack here, you just like jump up however much space you need for all your local variables for this function. And you store them all there while you're executing this function. When you're done, you just remove that from the stack and you're back down to your previous function and all of its local variables.
We're going to cover that a lot more in depth in these upcoming weeks.
Yeah, this is like a high-level overview, and then you're really going to start understanding this stuff when we get into like our Pwn lectures. Right now, I don't really expect you to understand it too much. Hopefully, get the general gist. Yeah, and then the heap, however, is when you like don't really know how much memory you're going to need. Like you might need 100 bytes, you might need like 5 gigabytes of memory. I don't know. So then what you can do is you can call a function malloc, and you can get some new bytes. You can just get a chunk of memory that is that big that you can now use. Then when you're done with it, you call free, and it gets, well, the one way to think about it is it gets released back to the operating system, which isn't really true, but that is what G. Carl Evans says. So I will say that. It gets released back to the operating system. And then, yeah, and that is like dynamic memory, and there's not a whole lot for us to do there. It's kind of, it would be very difficult to exploit. The next challenge, we'll talk about how to exploit a problem with heap allocations. But for this one, we're kind of interested in the stack because there's a lot of important stuff stored there. Stack frames. I talked about this a little bit. It'll allocate all your local variables. And then when the function returns, you no longer need those local variables. So it just goes back down to the previous stack frame. But how does the program know where to go, what like instruction to go to after a function exits? And the answer is it stores that in the stack frame when you allocate a new stack frame, and it's called the return address. So you can now jump. So since we can like write to a bunch of memory, like maybe we could write to the return address maybe. And that would be cool because now we can control where the program goes. Because I guess I didn't really talk about this either. There's an instruction pointer. The instruction pointer points to memory. That memory contains the machine code that you are executing. And we want to control that, because if we can control what machine code the program is executing, maybe we can get a shell or get a flag or something. Yeah, there is a slight problem with this. If we write a controlled value, the issue is we don't know what the program address is that we want to write because it's randomized each time where the code is. So maybe like some magic function that gives us the shell is stored at like address 1 on one run, but it's stored on address 5 million on the next run. And we don't know where it's going to be. So yeah, this is a problem that we'll need to solve. And here you can like see this is a stack frame dump from GDB, and it's kind of annotated. My friend annotated it with what the things are. So here's like the out bit stream, or the out string is part of the out stream, right? But yeah, here's the start. Here's like underscore start return address, libc start main plus 213 return address. So this plus 213, libc start main is like a function that is called on the start of every binary. You like initialize a bunch of stuff. Plus 213 is the offset that we're returning to when we're done with our current function. So we're going to, because it presumably called this function at like plus 212 or something like that. And now it's jumping to right after that. That's our return address. That is kind of what we want to overwrite. So now a really brief thing into how we actually get a controlled write. You may have noticed that this only gives us cloning a bit n times. It doesn't give us a controlled write exactly, and we're going to get caught out of bounds on the next time. However, what we can do is, because the size, if we go back here, mstir, well, so there's like, normally mstir is going to be a pointer to the heap, but there's this optimization that C++, libc++ does, where if your string is small enough, it can store it in line inside of your inside of your string, I guess, and it'll store up to 15 bytes. So if we make our size of our string less of our output string, if we tell it it's less than 15 bytes, then it will store it on the stack, and we get out of bounds right on the stack. And then we can overwrite the length of the string, mlen, with a larger number, because we can just stick a bunch of ones in there. And ones, if we stick a bunch of ones in there, it'll make it really big, and we won't fail our bounds check. And we can write essentially anywhere on the stack. And now we will want to write to libc start main plus 213, because we're going to jump to that at the end of our program. And if we overwrite this with a function that magically gives us shell, awesome. Now, how do we get a function that magically gives us shell? Well, I've highlighted this seemingly random, like magic number here. And this turns out to be the address of a function that magically gives us shell. The question is, like, how do we find this? This is not in the program that we are provided. This is in the libc, the standard library. So what we do is, this is kind of known in the CTF community and maybe the exploit dev community as a one gadget, because it's a gadget you jump to and it gives you, you've phoned the system. So essentially we want something that calls /bin/sh. So Ghidra has a useful thing called xref, which stands for cross-reference. And we can figure out where something's used. So we search for the bytes, /bin/sh in libc. We find that string present. We search for places it's used. We find this exec VE call within another function. And if we can jump anywhere within this function, if we jump like right here, it turns out argv and param3 are the correct values, such that this will simply just execute /bin/sh and be done. And then it will dump us inside of the shell. And that's awesome. We want to jump to this address. The final little like, I guess, trick you have to do is that, since I talked about how the addresses are randomized, you can't just overwrite the whole address. But if we overwrite part of the address, then we can keep the higher bits that we're still in libc. Because remember, this is libc start main, which is a function in libc. And then this right here is also inside of libc, this code that we want to jump to. So we know then on our stack, we know on the stack, some of this data is what we want. It turns out that libc is a little bit big, and there are some numbers we won't know, so this isn't going to have 100% accuracy. So that you think about it, like, we'll have like, I don't know, 1, 2, 3, 4, 5, and then you like, it's at an offset of like 20, 1, 2, 3, 6, 5. You don't know if we want to switch it back to a 4, that's an offset from the current value, and we cannot simply like do a partial overwrite to get it back to a 4. We just have to guess that it's like a 4 and then run it enough times and it will be a 4 eventually. So we do that, but with the address of our one gadget. So we only overwrite the lower like 3 bytes, and then we wrap it in a while true, and then we run it like a lot, and eventually it spits out the flag. Yeah, so it's hopefully, I don't expect you to understand all of that. Maybe if you're like already into this stuff, you kind of got it, but hopefully you got the general overview of like just all these different strategies that you use within pwn challenges in order to get the flag and, you know, hack the binary. Okay, so the next one, this was one more point, worth one more point, so a little bit harder potentially. And this one was a heap challenge. And I talked about how there wasn't really much we were interested in overwriting on the heap in the last challenge. In this challenge, we'll talk about what we actually are interested in overwriting on the heap. So dynamic allocation, I talked about this a little bit. You can allocate a bunch of memory, you can free the memory, and it lets you use memory without like committing to how much you're using beforehand, which is useful, for example, when you are like giving them a bunch of words that they need to store in memory and they don't ever want to run out, and they also don't want to allocate more than necessary at the start. So I guess the question is like, how do we exploit this? Well, with the heap, it's really easy to induce what we call undefined behavior, which is behavior that essentially all of this like language stuff, the free calls and the allocations, it's defined by a language specification, language standard that tells the people that actually implement the language what they should implement. And then there are cases where they don't need to care what happens. For example, operating on freed memory, where you've said, I'm done with this memory, I'm not using this anymore. So now if you do something with it, well, literally anything can happen according to the standard. You could like delete all the stuff on your hard drive, for example. That would be perfectly valid for the compiler to make it do. Obviously, nothing's going to do that because that would be a very inefficient way to implement that behavior, but That's the idea. So the thing is that we actually want to look at the specific implementation that is being used, which is libs stdc++, and which specifically uses glibc. And that, so we have, oh wait, this isn't C++, so this is just glibc. But the point being, we want to look at what the actual implementation is. So first off, does anyone see anything wrong with this code? I talked about how operating on freed memory is undefined behavior. So it will, yeah, if you trigger both of these if statements, you first free this, the value stored, or you first free the value in this variable, and then it frees the value, oh no, it like frees something at, so the array operator is just syntactic trigger for dereference A plus B. So it dereferences the value stored in this variable plus 1. The value stored in this variable though, well, this variable, this value stored in this variable got freed. It's freed memory. We can't dereference it, or else we invoke undefined behavior. So we're using memory here that like we don't know what it is. It could be anything. Well, it can't actually be anything. There is an implementation. There is real stuff here. So what we do is we look at what the implementation actually is. And it turns out it ends up, once you free it, it puts it inside a linked list. At the beginning of the linked list is this very, very useful pointer that stores, it has what are called the T-cache bins, which you can see here. And that's thread local caching bins. And we don't, I'm not going to go too much into the details of this. It's like quite quite complicated and quite interesting. And I think we do have like a T-cache thing later. There are like a bunch of challenges on the CPF thing. But the thing you need to know is that when you free memory, it doesn't actually get released back to the operating system. It goes into some bins called free lists so that the memory can be reused later. And that's more efficient than constantly shuffling it back and forth between the operating system. If you allocate some memory and then you free it, then the program can just reuse that same memory in the future rather than asking the operating system for more and going through the kernel, and like that's really slow. So essentially though, what this means is we get write access, 0x41, you can see some input will get us this. That's like the letter A. So we get write access to all of the free lists within the T-cache. And that means that allocation, if we call malloc, that will pull from the T-cache. And in this case, it will pull our own address from the T-cache and start using that as if it was allocated memory. And well, what we want to do is, I'm not going to go, so this requires a bunch of like funky, deep feng shui, and it's like very, it's something that you kind of learn. It's a large learning curve. It took me a long time to learn it. So I'm not going to go too deep into it, but we leak a libc address by, I guess the keyword here is like putting a chunk in the unsorted bin and then getting arbitrary read to read the libc address that gets put on the heap because of that. But we do that because we control the free list, so we control what addresses get returned by malloc, so we can invoke a bunch of weird behavior with the binary. And then we have free hook, which essentially gets called instead of free if it's set to a non-null value. This is just a variable inside of libc. We write that with system, which is a function that just executes a command. And now when we free a chunk, instead of getting freed, it will get passed the system. So if we free a chunk with the content /bin/sh, as you can see I'm doing here, well, that will get us a shell because it actually calls system instead of free. And then we can just pass the flag. Yeah, so once again, like kind of high level overview, a lot of words or a lot of concepts that you might not be familiar with yet, but you will be familiar with them if you continue attending meetings. And finally, this one's going to be like relatively brief because once again, it's a very in-depth thing. This is a kernel exploitation challenge. What is the kernel? It's basically like the, it's like the very, it's like a very central part of the operating system.
We'll cover it. We're going to cover a lot of the things that you've been talking about, like BACnet and stuff. Just real quick, this is some hard stuff. So if you're a little intimidated, that's okay. We're going to help you learn a lot of this stuff and a lot of the fundamentals that help you solve these challenges. But some of these things took years to learn.
Yeah, this took me years to like know all this stuff. But yeah, they like, I've been doing this for like a very long time. So I'm, yeah, like I don't expect everyone to kind of understand this on like a deep level. But eventually you can understand it on a deep level. Come to SIGPwny meetings because we're going to teach this stuff. But yeah, high level overview of what the kernel is. It does a lot of the operating system things. It handles the file system. It handles file system permissions. It handles distributing memory, mapping between the physical memory in your computer and what the program actually sees as the memory. It handles doing privileged operations like writing to memory or, I don't know, like executing functions. That's a system call that gets proxied through the kernel, or sorry, executing other binaries. Yeah. Some unprivileged programs, like the things we've been dealing with so far in cold and word games, they interact with user space. User space, each program gets its own virtual memory space where it's writing to a bunch of addresses and it just deals with that. It can't screw with any other programs. It's just all on its own. Kernel space, however, is like, it stores a lot of very important stuff, very sensitive or like protected stuff, like file system permissions. If you can write to kernel space, you can just make your whole file system writable, for example, and then do anything. And so the setup of this challenge is that there's a kernel driver that you can interact with, stored, loaded on a system, and you're given access to a virtual machine as an unprivileged user. And your goal is to read a flag file that you do not have read permission on. And essentially the route you're supposed to take is to exploit the kernel module in order to escalate your privileges and read that flag file. And there are a lot of ways, once you have write to kernel space, there are a lot of ways you can escalate your privileges and read the flag file. The way that I actually used is a little bit funky and like kind of a, I don't know, it's like a funny way that I'm not really going to go into because there's not too much value in knowing it beyond just like doing these CTF challenges. And it's something we can learn if we do like a kernel meeting or something. But it's not worth talking about right now because it's not that interesting. But what is interesting is how we get right into kernel space. So here's a snippet from the kernel driver, an IOCTL. IOCTL is a syscall. Essentially, you have this file on the file system. In this case, it's at /dev/crypto, and you open it, and you send stuff to the file descriptor that open returns, and it will do stuff. Crypto RNG command is 0x1337, and you'll see how we use that later. And then you have arg, which is passed in by the user, file passed in by the user. Okay, so here's how we use an IOCTL, which is what /dev/crypto is. We open /dev/crypto, then we use the IOCTL system call, and then the kernel will jump into the driver that we see part of the code of here, and it will do whatever it does, and then it will, yeah. And then call's done, yeah. So let's look at what it actually does. We saw that the IOCTL call calls crypto RNG with our user argument as params and our file as file. Essentially, so KZalloc is like malloc. It allocates memory, dynamically allocated memory, except this time in kernel space. Crypto RNG get bytes is another function that just gets some random bytes using a random number generator. And then memcopy copies memory. And it calls params, which is the stuff that we passed in. It reads the buffer, calls params buff, gets that value, and it copies stuff from kbuff, which we can see here is what was the random data was written to. So it copies data from kbuff into buff, where buff is a pointer that is passed in through user input. Does anyone potentially see a problem here? Wait, sorry, what? Go to out free. So if crypto RNG get bytes fails, if the return code is negative, then it's like done. It's not going to mem copy because the output of crypto RNG is meaningless. So then it frees the buffer because it's always going to free the buffer. Yeah. I don't know, like the control flow is basically if this function fails, just free it and return. Otherwise, do the copy, then free it and return. I guess. And then kbuff is just like allocated for as like scratch space for writing the random data. I guess. Yeah. Does that make sense? Or answer your question? Yeah. Cool. So okay, so the bug, memcopy, copies memory. Well, what if we put a kernel space address inside of params buff? Well, it'll copy stuff from kbuff into this buffer. This buffer is in kernel space. We are now writing to privileged memory, and you can do scary things with that. Yeah, so our goal was write to kernel space. Well, look at that. If we pass in a kernel space address right here as the, instead of &p, we put in like well, whatever the kernel space address is, we don't really know that yet. But if we do that, then we're writing to kernel memories. So memcopy. So, and the way you avoid this when you're writing a kernel module, like memcopy, you should never use memcopy when you're writing a kernel driver or a module. You should use copy to user, copy from user. And what that does is copy to user will verify that the pointer you're writing to is inside of user space and not kernel space. So if they use copy to user, there'd be no vulnerability. If they use memcopy, this pointer can be anything because it's user input, and you can write stuff to kernel space. So our first problem, we don't really know what a kernel space address is because it's random. And this is like a security feature that was added. They randomized kernel space addresses to make it harder to exploit mistakes like this. And so how do we bypass this? Well, it turns out in the VM they give us, when the syscall fails, the IOCTL syscall fails with a invalid memory write, all it does is just kill the program and you get a return code -9 right here. And so there are like chunks of memory that are writable, and we now have an oracle that tells us, is this memory writable or not if you pass in an address. So we just iterate over a bunch of addresses. All the addresses is like not quite true because there are like 2 to the 64 addresses, but we iterate over chunks of addresses that within kernel space that will tell us where the first writable address is by just kind of binary searching down once we get this kind of, like we get like this many bytes and then we have this many to figure out, and you can just binary search that. So we run this Python script, we get out an address, and yay, now we have an address that we want to write to. So we just plug that into our program, right? And we write the data, and yay, do we win? Well, no, not really, because kbuff is written to by crypto RNG get bytes. It's an RNG. However, if we look at the crypto RNG code, you will see that it seeds it with 0. So it actually has a constant output, the random number generator. So our problem, we can only write random bytes. However, the seed is constant. So this number, the random bytes it outputs are constant. So we can know ahead of time which random bytes we want to write to the thing, and we can just throw away the other ones by writing them to some junk address. And you can see here my code to get the bytes that we want. We have desired = /temp/k, which is a useful string for the specific exploitation method I use to get root privileges or to read the flag. But yeah, point being, IOCTL 0.137. If the written byte is equal to the desired byte, then I just log the index, and then at the end I print out all the indexes that I want. And now what I do is I write these indexes to the address that I want in kernel space. And then I have arbitrary write to kernel memory. And in kernel memory, there are all sorts of important things stored, like file system permissions. One potential solution could be overwriting the root file system permission bytes to make it globally readable, and you read the flag. That's not what I did, but yeah. And I don't know, does anyone have any like questions? That was a lot. Yeah, those are like 3 very difficult kinds of phone challenges: C++, heat, and kernel.
Kevin really came in clutch and solved most of the phone, which was huge because the phone was really hard this year. So for real, thank you for coming in clutch, and thank you for those explanations. That was really cool. All right, let's update these. Cool. Zoom, we're still good. I'm gonna plug in my computer. That way the meeting doesn't get derailed. Also, as these are like Sunday meetings, there's no official end time. So like technically we've gone past an hour, but the meeting doesn't necessarily end.
Sorry.
In that, no, you're good. You're good. You're good. You're totally good. We want, honestly, this is content, right? Like we can go take this and we can put this up on YouTube and people can watch it, which is awesome. Cool. Plugged in. Go ahead.
Okay. All right. Hello, everyone. My name is Pete. I'm a freshman here. I'm pretty new to security, but CSAW was fun. And I had a lot of practice with the internal CTF. And yeah, I'll just go straight to it. So we're given a forensics file system of a Windows machine. So it gave us this like registry files, all the user profiles and stuff, as well as scheduled tasks. So while we're poking around in all these files, we found a very interesting scheduled task. So the energy conservation program, all it does is runs a PowerShell script, which isn't exactly what I think Microsoft wanted to happen. So let's take a look at this file. So we take a look at this file and we see it downloads actually a string from Pastebin, and then it does some replacements. It also finds a password from the registry keys, and then it decrypts the contents of this file and outputs it to this fate.exe file, and then it runs it. So let's take a look at that. All right, so after some analysis, this took us a while, probably too long, but we eventually figured out it was running a Python script. And up there in the top right, I've shown a little thing where we just ran strings, and you can see all these Python related things happening. So we analyzed it in Ghidra to determine it was running Python. And after a lot of trial and error, we figured out the exact tool they used to compile the Python into an exe. And we were able to use another tool to reverse it back to the original Python bytecode. Unfortunately, once we got the bytecode, the header, so basically what tells the computer what kind of program it is, was corrupted. So we manually had to figure out the correct Python version and edit that header so it was a valid compiled Python file. And then finally, we were able to use another tool to get back to the original source code.
This is probably like 4 or 5 hours of just trial and error.
Okay. Oh, all right. Do you want to do the slide action?
Yeah. So once we get the Python source code, there's a lot of stuff going on, and you can see it's both in the challenge description and in the code. There's these functions called, referencing something called DNP3. So if you Google DNP3 is a protocol for process automation, which is like electric power grids and then like water lines and stuff like that. So I don't know, I thought like the lore for this challenge is kind of interesting. And this protocol has something called breakers, where you can send a command to like an electric grid or like a water pipe, I guess, and tell it to turn off or trip a breaker. And the purpose of this challenge is to figure out how many times substation C, which I don't know if you can read that, it's like substation _C over there, is sent a command that tells it to trip a breaker. So what we have to do is we have to find like this DNP3 protocol. It's like a 100-page PDF. There's like 20 relevant pages that we have to look at. We have to figure out when we send what bytes, how does that what bytes affect the breakers and stuff like that. So for about like an hour, we read through the protocol. We tried to figure out when is the code tripping breakers. And what's going on here is that in this packet, this very first DNP3 packet that it sends, that is sending a trip breaker command. And basically what we did, you can kind of see it there. We just commented out all the like networking code in here, and we ran the code, because it's just a Python script you just run down on your computer, and we counted how many times that like socket was meant to be sent, how many times that packet was meant to be sent over. And what was the number we got? Like 200 something?
Yeah, it was 200. So the major part of this was the understanding of the protocol and not actually the script needed to count the number of packets sent.
Oh. No, one more, there it is.
All right. And then finally, you can put this all together. So it asked for 2 pieces of information. What was the IP address of substation C? And on the previous slide, there was code for that. It's kind of a little hard to see.
Yeah,
sorry.
but
And then also wanted to know how many breakers were tripped. And then we put that together in our flag format, and we got the flag. And we were one of 58 solves in the challenge. So I'm pretty proud of us for doing that. And then on the right, it's kind of covered up by Zoom, but there's a scheduled task that called the PowerShell script. Scheduled task that calls PowerShell script that calls the exe, which runs the Python script. So after all those steps, we were able to get the flag. And that's it.
Mm-hmm. I think this was the challenge that PPP hadn't solved for like the last 10 minutes. We were like neck and neck with them, and then they solved this. But
Yeah, we were 18 points ahead with like what, 20 minutes left?
yeah,
18 points behind.
18 points behind, and then they solved it.
Well, yeah, I think that's the last slide, Thomas. If you want to take over.
So just look at action.
Yeah.
Cool. So. Hello. Hi, Zoom. So next week, thank you all for sticking around. I have no idea how many people are left. Cool. So thank you for sticking around. Next week, we're doing Crypto 1 and Crypto 2. So I'm not totally sure how accurate the topic list is here, but for Crypto 1, it'll be the fundamentals of cryptography. So symmetric and asymmetric key encryption, what's the difference between those two? How people will communicate with each other in safe ways. The CIA model, which we'll talk about. And then we're going to cover, in terms of practical crypto, Caesar cipher, Vignere cipher, and probably really easy RSA. And then over the weekend, we're going to start looking at some other things like frequency analysis and other ways to kind of start to break the crypto models that exist. And then we might also talk about ECC, which is elliptic curve cryptography, which there was a challenge for that here. So thank you all for coming. That's the meeting. Thank you, Zoom. I'm going to stop the recording. YouTube, like and subscribe.